So let's start. We have the last lecture of QBI today. There will be the project presentation, and I will come back with that information about the plan in 2 weeks. So yeah, today we are going to talk about how to handle the amounts of data. So it's a more computational approach on the lectures, and yeah, let's see what we come up with. So one thing is we are going to get into more computer science and computer system organization, and also mentioning some tools for big data handling. And in the end, I will also give a little bit overview of what we have talked about during the whole class, but that's not on this outline. There is, of course, always some information. There are some links. Honestly, I haven't checked if these are up to date, so it could be that they have changed a bit. But the information should certainly be around somehow. But yeah, sorry for the inconvenience if the links are not up to date. Also about cluster computing, there are also some more information, also local information like the cluster locally here at ITET. And yeah, that's about that. And there is also a little bit about different databases and cloud computing. So there is a lot of reading if you're interested to go deeper in the topic. And well, now we come to the motivation. And there are different types of problems that we can come across. One is that we have really big data sets. So they're not fitting on a hard drive. They're not fitting on, maybe not even fitting in a server rack. That's really a big problem if you're going to analyze that data. You can also have many different data sets, and maybe you want to do some exploratory study before you start forming your hypothesis from existing data. So the really big data sets, to process it, there is the problem that it usually doesn't fit in your computers. You need a strategy how to work with it. And there are workstations around with 256 or even, I think now you can even get up to 1 terabyte of RAM memory. But if you're going to split up the task on several cores, in this example we have 256 and 16 cores, that would give you 16 gigabytes per core to work with. So maybe that is too little, depending on the data set size, and actually also on the strategy how you split the data. Also, another thing is the drive speed. How fast is your hard drive? That can be actually a bottleneck, or even worse, if the data doesn't fit on your hard drive, even how fast can you access the data from the network? Another problem that can be coming up is if something crashes, you have to somehow handle the fault tolerance so that you don't lose everything you have done until the point when it crashes. In particular, prototype code that you make during your projects, they are not always so stable as you could wish for, so there is a risk that it crashes, and then it's important to have at least some kind of checkpoints on the way to handle the thing. And writing that on your own, that can be quite cumbersome, and if you can avoid it, it's better. So if you can have a system that handles the checkpoint, that is a good thing. Then you also have many samples. There are some genome studies with thousands of samples, and you have to handle them. and they need to be analyzed in the same way. Also, in dynamic experiments, you want to follow a process, then you have also many time points that you want to analyze, and of course they need to be analyzed in the same way. And well, you have also cases when you have the phenotyping. You need a lot for biology. You need a lot of data sets, and it could be, for example, here thousands of over 300 gigabytes of data that you need to handle. And just as kind of a fun fact, the radiologists in Switzerland produce about a petabyte of data of scans per year. So that's quite a lot of data that is produced also in the hospitals. When you go to a data set in the beginning, if you didn't do the experiment yourself, but you got some data set that you want to explore features of, you want to do some first exploratory analysis to get an idea what you're up with, and also start planning a little bit on what kind of analysis workflow you're going to use. But you need an easy way to at least develop new analysis structures or quick test some hypotheses and on this data. Then we have some project examples here. The zebrafish animal phenotyping. It's a lot of CT scans of full-sized fish, and the resolution is quite high, so it's below 1 micron, and plenty of those tomography data that needs to be analyzed. And you can see here that you have about 20 to 40 gigavoxels per sample, and that is already exceeding what you can have in a normal laptop if you want to have the whole thing in the computer. So typically what is done is that you take it in chunks and analyze it separately. And here the objectives would be identify single cells without any downsampling, so we would have to work on the whole data set. Maybe also look at cell networks and connectivity. Further on, classification, which cell type there is, and some registration tasks. So there are quite many tasks that you could do on this data, but it's not easy to squeeze in your computer. The brain project, if you want to also study the brain on cellular resolution, you need to go down to 1 micron resolution, and already 1 cubic centimeter gives you 1 gigavoxels per sample. So then you can imagine how much the whole brain will take, and then from several individuals. And there you want to first register the scans together. You want somehow to identify regions within the brain and compare them between. Also looking at blood vessel structures. Now we come into doing skeletonization. Potentially also looking into functional MRI and register that to the data. And histology data could also be something that could be interesting to relate to. So we have some workflow that we have been working with throughout the class. So for example, I want to do this kind of workflow where I read the image, I do some medium filter and threshold afterwards, and label it, and then compute the histogram, and to get the count, and then write out the results in a file. Now if you want to change this, you have to actually change the code, and that may not always be the easiest to do on the fly. So what we want to have is some kind of higher level description for the pipeline. So that brings us back to the pipelines we did in, was it lecture 6, I think, or something like that. So we describe it instead of as a program, as a parameter file, and these parameter files are easier to modify on the fly. So if you want to compare different use cases, Gaussian versus median, maybe 3D instead of 2D, and maybe also run the whole work on a folder of images instead of a single one. And typically, if you just have a program like this, you have to rewrite it for every use case and run separate programs, which is then inconvenient. And this is also important to think about if you start working with larger data sets, that you have to have a good plan of what you intend to do already when you start sketching up your workflow design. And otherwise, you may paint yourself into a corner, and it's very hard to get out of it without a lot of work. And what we can do to prepare our workflow is one thing. The first one is to handle chunks of data instead of whole images. So we say, for example, I want to work with 100 by 100 pixel chunks and send that into the processing. You should also work on structured code that you can define some pipeline. And when the data grows, it's of course interesting to do parallel processing locally on your own computer, or even distributed on a cluster, or even larger distributions. The data format is really an important thing. Not only if you use TIFF or JPEG or whatever files you use, but also how you organize the files, in which folder structure, because that will make your data handling more or less difficult. Typically, if you have volume data, often you get just slices. You may also get volume files, which is to prefer. Because when you start reading a file, there is a little overhead. And every file you read costs you some overhead. And if you have a volume file, then you only open the file once, and then it's easy to access the data, and that speeds up things quite a lot. So it's a lot about time. The more data you have, the more every millisecond counts. And then also containerization and environment reproducibility is when you have written your things, they work on your computer. Do they work on your friend's computer? Do they work on the big cluster? I don't know. So the containerization and environment is that you have a little description file that describes exactly which packages and which versions you intend to use. And with that, you can just deliver this file and say, if you install this, all is good. And actually, I have done it so also on the GitHub repository for these lectures. There is a little file called pixie.toml, and that file describes exactly which packages are used to prepare all these notebooks. And that makes it also possible then to port it somewhere else. Then, of course, there is, I didn't mention it here, but also the difference between different operating systems behave differently, have different versions. That is something you also have to test if you want to distribute things. Finally, also, it's always good to have some logging to know the state of your processing and give you an idea how far you have gotten. And the fail safety is, in case something crashes, it should be made some note that this piece needs to be reprocessed, or at least logged and noticed that this block wasn't possible to handle. And if you crash at a certain stage, it should be possible to restart the process from that stage, or the stage before, not to do all the things that were done before that point. And now for this, we walk over to the computer science principles. And the first things that we need to do, as we are talking about doing things fast, is parallelism. Then we come to distributed computing, resource contention, shared memory, race conditions, synchronization, deadlocks, different programming styles. And of course, now within half an hour, I will not be able to cover this on depth. That would be fantastic if I could do that, but no, not. I'm just giving you a hint of different pieces, what you can do. So the first thing is, what is parallelism at all? That is when you can divide your task somehow into subtasks or split it up in chunks and work on them at the same time. A basic everyday topic is you want to walk and you want to talk on the phone. There are different ways of doing it. One is walking and then stopping and talking on the phone. Each takes 5 minutes, so you would have consumed 10 minutes for that. More efficiently is that you walk and talk at the same time, and that would take 5 minutes. So you have actually reduced by the working time by halving it. So that is a way of seeing it. Of course, you may not walk as fast when you talk, because you have to consider 2 things at the same time, and that can be quite difficult sometimes. Anyway, that is what the idea is, and here is an example. I was running on my computer a process during my testing. First, I ran it in parallel, and you can see that there is a high peak. And then I started the exact same processing on a single thread, and now this bar is more or less lying down instead, so it took twice the time as I was doing it in parallel. So it can be done much faster if you try to use all the cores. There's always written on your computer, or the sales papers say you have 16 cores and you have 32 cores or whatever. And many code, in particular Python code, is running usually on only 1 core. So it's not very efficient unless there is a backend that is written for faster processing. And of course, the speed or how fast you can do it depends very much on the implementation. And if you want to dig really deep into it, you can watch, I think this is a video, yeah it is, a lecture by Scott Myers, C++ guru, and he talks about the relation between how the memory is handled and the speed of your code. It's a very interesting lecture actually, if you want to look at it. So let's look at the median computation. Here we have the task. You have some friends, and each friend has some coins, and you want to know the median value of these coins, or the histograms from them. And first, what you can do is you ask each friend to make a histogram of which coins they have. Then you get that one back, so you have a lot of small histograms. And then afterwards, you can make a reduction, so you just sum up all the results for each bin into a histogram like this, and from that you could in principle compute the median value of the coins. So this is one way how you can see a parallel processing. And the question is also how easy it is to make a task in parallel. There are in different ways of describing. We have the embarrassingly parallel process, which is essentially every pixel or every region is independent of the other ones. So you can just say you have 100 by 100 pixels. Then you can split it up into, say, chunks, 10 by 10, and each can be processed individually. The neighbor doesn't care about the other one, and that is a very easy one to parallelize. Then you have coarse-grained. That means you need to interact at least with the neighbors, for example, getting the boundary conditions right. So one example, which I'm going to show also later, is when you do filtering, and the filter has some certain width, and you come to the edge, and usually there is some kind of edge processing, but that is mostly some kind of mirror of the edge effect. But you actually have a chunk as a neighbor where you could fetch the information, and that information you want to send over to as edge processing information. And that is where we get to the coarse-grained, and then the fine-grained parallel. Then it's really you need to talk to all the items in crosswise, and you have a lot of communication between all the processes. That is harder to parallelize. So, for example, looking at labeling tasks, they are harder to parallelize than just a thresholding, for example, which would be here. And then when you start doing things in parallel, you expect some speed up. Ideally, you would expect that there is a linear relation between number of cores and the time it takes to process with a single core. That would be the nicest situation. However, there are different things that how fast you can run. So one is available resources, how you implemented it, how it's scheduled in the CPU and the operating system, and overhead. So typically, what you have is that if you look at this line, that would be the ideal one. But in the reality, it often looks something like this. And interestingly, it can even go down. That is slower to work with more processes. That is because of overhead and available resources that can bring it to go down. And also here you can see the processing time. So at some point it's good, but then all of a sudden it takes more time. And one resource is actually on the deep level that the cache has problems to keep track of everything, and that can cost you a lot. I have examples where I tried to parallelize on 10 cores, but it was slower than a single core. It's possible that that can happen. So parallel is not a free lunch. You have to work for it. Performance experiment run. I want to see where I had the hotspots in my code. So what I did, I added timestamping for each sub-task in the processing. And then I ran it for different dataset sizes. And in the beginning, it's barely visible in this plot. But then you can see that things are going up. And the purple is obviously very time-consuming in this process. So then I identified, okay, this one I need to put more energy into to make faster. And then I introduced the parallel code, and all of a sudden, this one turned down to a fraction of what it was before. And then I was happy, at least for the moment. Another thing you have here, which we will come to on the next slide, is the theoretical speed up, because you have parts that can be parallel and parts that cannot be parallel. So that's the sequential code. And Amdahl's law is written as this. You have the amount of parallelizable code, and then you have, no, this is sequential part, and this is the speed up you can expect. And here it can tell you essentially what you can expect with your parallelization effect. So if you have a long sequential part, it doesn't matter how much you parallelize, because that one will be dominant in the end. And that is what you can see here. In this code, we have the yellow blocks. They will be constant all the time. And no matter if I bring this part down, this one will still remain constant. And there could be things like writing to file is usually a thing that you cannot parallelize very easily because you only have one drive. Maybe you have some parallel channels on it, but in principle, writing to file is something that is hard to parallelize. You can also have synchronization components around that delays the whole process. And that is where we have the problem with the resource contention. You have different pieces of information that you should handle. You have the access to memory and files, and you have the network resources, and they will actually delay or be, in the end, be pretty dominant when you start parallelizing. All this, or these two, can be improved if you have a cluster or distributed system, because then everything is distributed, but and also the network will be optimized. It's not the normal office network that they're using in clusters. They are highly cross-wired systems, so it's made to do good communication between the nodes. And the challenges we have is coordination, that you make sure that things are happening in the right time. You could, for example, have one thread only working on reading and writing, while the other ones do the computation. And then you always have the data ready when the computation is done, and with that you can run those parts in parallel. There are also the problem that two devices want to write on the same spot or work on the same data, or one writes and the other one wants to read it, and you never know exactly what timing, so you have to have some blocking mechanism that protects these areas. And that brings us to a classic problem, which is called deadlock, and that is when two are trying to reach the same point, but they're a little bit interleaved with different requirements, and it's usually described with the dining philosopher's problem, an anecdote where you have some great philosophers sitting around the table, and they should eat, but to eat they need to use two forks, and there is only as many forks as people around the table, so now they have to find out which philosopher can start to eat first. And the beginning is everybody takes the first fork to the left, and then realize, oh, it's empty. So then they put them back, and then they have to find a solution how to coordinate themselves in order to have someone eating and not everybody starving. And then they have to make a good plan around that. Then when a single computer is not sufficient, then we go towards the distributed computing, and then you can parallelize this on a larger scale. And distributing it involves a lot of new implications, like network delay, depending on where you have the computers. It could be just in the same server park, then it's pretty good. But if you start having different server farms on different places, then you can have problems. Also, the file system is a problem because you need to make sure that all these computers work on the same data, so they need to have a central server with the data that they can access asynchronously without blocking each other. And another thing with distributed computing, these computers are so big that not only a single user are using them, but several users, and they also want the resources. So say someone wants 10 units, the other one wants 20 units for their processing, and then you need to have some kind of scheduling system to make sure that everybody can do their job. And some distributed computing examples. Let's say you have 10 friends, and all these friends, they know all the capitals in the world. Not necessarily that one knows everybody, all the capitals, but collectively they know it. And to find the capital of a single country, it's quite easy. Then you just say, I want to know the capital of that country. Everybody got the request, and some respond, and you take the first response that you get. To find out who knows the most capitals, most countries, then you have to ask everybody how much they know, and you select the highest out of those. You need some central code to handle that. And the other example would be each friend has some money with them, and to know the total amount of money available, you ask everybody, how much do you have? And then you can sum it up. To compute the median coin value of everybody, then we come back to the example I showed with histogram before, then you have to make some kind of list or a master list telling what how many coins there are, and then you can sort it. Or with the histogram example I showed before, everybody can deliver some pre-sorted information, but you have to merge it at least to get the median. So when we do this distributed computing, the problem is a lot around the communication. So that is sending task and instruction data far away. So sending data far away is always a problem, because you may want to send terabytes of data, maybe between different computer farms, and that will take time. So the question is, if you send all the data, only fractions of the data, how to handle that? That's a strategy you have to make up on your own. What is the most efficient for your problem? Then fault tolerance is when you have all these computers, they are doing a lot of computations, but if one fails, how sensitive is the outcome when one fails? And you of course don't want the whole job that you sent out to crash just because one failed. The rest of them could have done something that makes sense still, but then you have to do some nice logging, or actually maybe resubmitting that subtask to someone else who takes care of it. And of course, when you have the data storage, you have to handle distribution in an efficient way. One way would be to have a local hard drive on each node, but that will be quite expensive, so that's why they're turning into using server farms with the storage. So now we'll leave a little bit the hardware for a while and talking about programming styles. We have two ways of programming. The imperative programming is you give the order of examples, the order of commands in a given row, and it will be handled in that order as you say it. Also, data management is manually controlled, and all the job and task management is manual. There is, however, potential to tweak the performance in this code, but with a lot of work, of course. But optimizing is always a lot of work. And from lecture 1, I showed the example of making a soup and we went through the whole recipe, what you need to buy and what you need to do and everything, and then you let it boil before you add the meat. So this is really line by line recipe. If you use the declarative way, then you have the other languages that you work with. So that would be SQL, Erlang, Haskell, Scala. Python and R can be declarative, but it can also be imperative. The goals are stated, so you say what you want to achieve, and then you label that as some kind of state. And the data in this case is automatically managed and copied, and the scheduling is automatic in these systems, but may not always be efficient. You can probably also add a little bit hints on where to put the order, but typically it's handling in the background. So the declarative way is that you declare that shop veggies is, and here you have the task, then you have this task, and here comes the interesting part, that wait for the vegetables to be bought and before you do something, and then that brings you into a new state which says you have chopped the carrots, or you have chopped the potatoes, and then you have to wait for boiling water, and then you and chopping the vegetables, and then you add them, and then last step you wait another 5 minutes and add the meat. So it's a little bit different. You wait for things to happen before you execute the next step. And there are different ways how you can parallelize this, depending on these two paradigms. One is a question what you can do if you have a team of people to cook. If you have several people and want to make an imperative soup, then you say, okay, it's time to buy things. Everybody go hand in hand to the shop, buys it. The next one, they stand in front of a pile of carrots and they all start to chopping carrots and so on. So that is one way. And the other way is to do a declarative soup, would be that you, in principle, send off different processes with each of these tasks, and you wait for the task to signal, I have done it, and then it continues on the next state. And here, if you do the imperative, you can optimize specific tasks, and or you can also do many soups at the same time. So that would be independent, that everybody stands with his own pile of vegetables and meat and does something. So that would be the other way. With the declarative way, you run everything at once, and each core or computer takes the tasks and run it. And here the execution order actually doesn't matter until you come to the synchronization point. And then you just wait for the things to be available. So that's the synchronization then. Another way would be to do lazy evaluation. So you don't run anything at all, but you go backwards, actually. You say you want the soup, and the soup tells, I need to have boiled potatoes, and then it does the boiling, and then the boiling says, I need to have chopped potatoes, and chopped potatoes says, I need to have that the potatoes are bought. So that would be the other way around. And that means if there are no requests for tomatoes, they will never be bought. Instead, if you look on the other way around, you may have bought the tomatoes, even though they're not needed. Organizing a system is also a big challenge. And there we have seen in the lectures that all our processing results in a lot of result files. For example, if we measure cell sizes, we may end up with some kind of text file saying cell 1 had the size this one and those metrics. And all these files can be difficult to organize, and MATLAB and Python and also R and other languages. They're designed for doing the processing in memory. And sometimes these data sets, they can be very complicated how they handle together. And the data, well, saved as spreadsheets. In the beginning, it's very easy to go to make a spreadsheet, but it's not so convenient if you want to scale up things. That was a bit strange order. Okay. Anyway, Q computing is actually when you come up in the big systems where you have these clusters or server farms, then you have different units that you are talking about. We have the resources, we have the jobs, and we have the users. The resources are computers, memory, and storage. So we have a collection of processors which is associated with each with memory and local storage. And then we also have different network connections and potentially also special resources like printers. And all these resources, they are just giving you for a certain period of time. And this is the hardware that is available. Then you have the jobs. That's actually the task to process. And a job specifies exactly which task you want to run. And also you can provide information about the resources that you would need to run it. And in some cases also saying, this is the expected execution time of this job. And that makes it possible to schedule in the system. Then we have the users. These are the people who submit the jobs. They have accounts on the computer. And here we have to have some kind of democracy that people are getting more or less the same resources within some given time, so that not one is getting all the cluster for 3 days, then the other ones will not be very happy. So that's the task of the scheduler, to see that all these tasks or jobs, they are interleaved in a way that there is some kind of fairness among the users. The fairness can also be a little bit weighted with how much you pay. So if someone has invested a lot in the cluster, they usually claim also more of the resources. So a cluster has a certain structure. We have a head node or login node. This is a place that the user sees. And this is also the one that coordinates how things are distributed around the cluster. Then we have the compute nodes, which are actual computers. And the scheduler works in tight interaction with the head node, making sure that resources and jobs are distributed in the right way. And the networks is an essential part in the cluster because the computers need to talk to each other. So that is really important to make sure that the network is fast and not overloaded. So it needs to have several channels. And also very important is to have a shared storage in the system, so all nodes can access the same data, or at least fetch from the shared storage onto the local, because it's a little bit faster than always fetching it from the network. So this is, I would say, a good point for a break, and then we continue.